Whenever you see that, we say that the molecule has a plane of symmetry or a mirror plane, and it must be achiral. Notice that I didn't consider the carbon, carbon 3, or the iodine or the hydrogen, because they actually lie in the plane. So this plane, which is just two-dimensional coming in and out of the paper here, that contains the iodine, the hydrogen, which would be directly behind the iodine, and the carbon. And we don't take into consideration the things that lie in the plane. We just simply look at what's on the right and what's on the left, and we compare them, and if they're identical, if they're mirror images of each other, then the molecule has a plane of symmetry and must be achiral. So this is an achiral compound because of this plane of symmetry which runs right through the middle. Then we compare it to this alkene. We also looked at this alkene a moment ago, and we decided that this alkene is in fact a chiral compound because carbon 3 is in fact a stereogenic center. Well, if we think about that very same plane of symmetry that I just described, you can draw the plane, but it's not a plane of symmetry. While it is still true that carbons 3 and the iodine and the hydrogen would lie in the plane, what's on the right side of the plane, namely this ethyl group, is not the same as what's on the left, an ethylene. There is no symmetry plane here. There's no mirror plane. The molecule does not have that plane of symmetry, which is a important thing to know because it suggests in the absence of any planes of symmetry that the molecule could very well be chiral, and this one is, of course, chiral for all the reasons we've already discussed. It has that stereogenic center. It has only one stereogenic center. That's going to be a chiral compound. Finally, let's look at these two cycloalkanes we were just discussing a few minutes ago. This is the one we said did not have any stereogenic centers. And that's because the path around the ring in this direction is exactly the same as the path around the ring in that direction. You encounter exactly the same things and at exactly the same times, regardless of which direction you walk around the ring. So we don't treat those as different substituents, we treat them as identical substituents. This carbon right here, carbon 1, is bound to two identical substituents, therefore it's not a stereogenic center. The molecule is achiral. But another way of looking at that is to consider the plane of symmetry, which once again would run perpendicular to the plane of the paper. Perpendicular to the plane of the paper. It would include the chlorine atom, carbon 1, the hydrogen atom, which is back behind the chlorine. It would also include this carbon atom on the other side of the molecule. That would be carbon 4, 1, 2, 3, 4. And the two hydrogens, which weren't shown, but I'll go ahead and show them now. One coming out of the plane of the board and one going back behind. All of those atoms, so that's 6 atoms, the two hydrogens, the carbon, the chlorine, and the hydrogen, they're all in this plane that I'm talking about. And it is, in fact, a plane of symmetry because on one side are these two methylenes, and they are exactly compensated for, or there is a mirror image, if you will, these other two methylenes on the other side of this mirror plane or plane of symmetry. That's what makes it a plane of symmetry, the fact that this side is identical to that side. But when we move down to this molecule here, I don't have that any longer. This is not a stereogenic center, for sure, because it's bound to two of the same groups, two methyl groups. But this one is a stereogenic center now because the path around the ring in this direction is different than the path around the ring in that direction. And that plane, which we can still draw, is no longer a plane of symmetry because it still will contain the chlorine, carbon, hydrogen, the carbon and two hydrogens, just as it did over here. But this side is no longer the same as that side. It's not a mirror plane anymore. And therefore, this is not a plane of symmetry. It's just a plane I happen to be drawing near the molecule, but it's not a plane of symmetry. This molecule is chiral. So another way of thinking about chiral and achiral compounds relates to planes of symmetry or mirror planes. If you find a molecule that has a plane of symmetry or a mirror plane, it must be achiral. On the other hand, if you can't identify any of those, then there's a good chance that the molecule is actually chiral. This is hexane, simple alkane. Is that molecule chiral? Well, there are no stereogenic centers. All I've got are a couple of methyl groups and methylenes, or in other words, all of the carbons present are bound to at least 2 hydrogens, if not 3. This is an achiral compound. It's a molecule in the absence of any stereogenic centers, almost certainly achiral. If it's achiral, where's the plane of symmetry? Well, it turns out in this case, the plane of symmetry is the plane of the paper. You can see that all the carbons, at least as they're drawn in this particular conformation, lie in the plane of the paper, the very paper I drew the molecule on. The only thing coming in and out of the plane of the paper are the hydrogens, but you can see that there's one hydrogen in front, and one in back, and one in front, and one in back, and one in front, and one in back. And so if you think about the plane of the paper, everything in front is exactly the same as what's in the back. The hydrogens in the front have a mirror image behind that plane in the back. The only thing that's a little bit trickier to figure out are these methyl groups here. If you think about that plane, in this particular conformation it works, but I can draw it in a conformation that's a little bit different where it might not necessarily work. But the key thing to remember is that these carbon-carbon single bonds are rotating very rapidly. These hydrogens on this methyl group are like a propeller, and time average they spend just as much time on one side of the plane of the paper as they do on the other side. So time averaged, it is truly a plane of symmetry. So this molecule does have a plane of symmetry. It is the plane of the paper, and it is achiral. So there's multiple ways we can think about chiral compounds and achiral compounds, and multiple ways we can identify them, and we've just gone through quite a few of those today. So I hope this was useful to you. When we come back on Monday, we're going to continue the discussion. Please go ahead and work on the homework problems. You now know enough to do so, and I'll see you Monday. Have a great weekend.